Okay, next up we're going to run some simulations on this, but I want realistic simulations. You notice that I don't have any simulation data in here. I don't have any spice commands. This is on purpose, and it's a good idea. What I'm going to do, make a new cell, of course. It's a schematic cell, and I like to prefix these with test underscore, let's say XOR. Okay. What I noticed that I forgot, remember how we have in our icon here it says X1. Our icon for the this XOR gate does not say that. I'm going to go ahead and add that text here. Okay. I'm going to say X1, anchor on the left side, and say OK. Text is a little small, but it is the same as the other one. I'm working on EC429. Okay, and now we can go back to our test schematic. What I'm going to do is I'm going to drop down my XOR gate that I wish to test. And then I want to test this in a realistic situation. What I mean by that is I want to drive the waveforms that drive this input node. I want them to be the right shape, or the shape that's realistic. Easiest way to make a realistic shape is to use some inverters, because we know that the output of these inverters will be the right shape. Right, so wire these two up so it looks pretty. Yeah. Oh man, am I on a half grid? I'm on a half grid, that's so terrible. Okay, we're on 0, 0, 0. Okay. Oh man, that could have been bad. What's my icon look like? Left, that's okay. Just about had some problems here. Now my inputs for this gate, they're actually these two nodes, or arcs in electric. So I'm going to call this one A, and call this one B, and those will be my inputs. We'll drive these here in a second. Now on the output, I want to drive something that's realistic. One thing that we can do is just drive a base inverter. This is my X1 inverter. Hook those up. I'm going to call this node out. And now these names are going to show up in my spice simulation too, my LTspice simulation. If I want to do something crazy, I can select this instance, and I'm going to call this INVX1, and I'm going to have many of these, specifically 4, 3, 2, 1, and 0. I'll have to move this text here. I think there's a way to get that text to show up in a decent place, but I forget. Alright, now there are 4 inverters doing this. We would say that this gate has a fan out of 4. Okay, fan out of 4. If we do for 1, 2, 3, 4, you're going to be maybe simulating what these fan outs look like, or what the delays are when the load increases. That's a good way to also see if logical effort, the technique, is legit. These inverters, because the input of the inverter is not affected by what's at the output, we're going to leave these nodes open and not worry about it. We just want to make a nice environment for our device under test. Just to set that down, I'm going to say a annotation text, DUT. I'll make it nice and big. Blue, and I don't know, 25. Let's make it bigger. Whoa, I wonder. Apply, okay. It's still text size 30. Oh, because it's in units instead of points. Triple size. Beautiful. Device under test. You can use this then as a template. You just delete this, and then now you have your wrapping stuff. Let's make some inputs. So we want to put two pulse sources. Here's one. Here's another one. If I look at these things here, I say expanded, unexpanded. Okay. Edit parameters. Oh, there's an option in here that I forget about. What I was going to do is I'm going to come in here, zoom in here, and you see how these all look nasty? Like it's all tangled up. I'm going to select these. So I'm holding down Control and select that, Control, and then Shift, hold Shift click, I can't say it. Okay. Now my anchor is right there. Control I, which is properties, object properties. I can change these properties all at once. I want to put my anchor on the left side is what I'm trying to do. Say OK, now they're all nicely lined up. Initial voltage, pulse voltage is going to go to 5, 10 pico, rise and fall times, pulse width 3, 6, DC voltage is not useful for our simulation. Take this thing, Control C, paste it. See how the graphics worked out okay. Alright. Why didn't we do angly? What mode am I in? See how it's not... Oh, because I'm drawing other stuff. Not sure what I'm doing wrong here. I don't know. Components. I'm going to draw not a wire, an arc, a wire. I don't know why it's not keep forcing the rectangular. There it is. For some reason. Alright, put my ground node here. As you know, there can only be one ground node. They are hooked together. If I hook, you can see that there's hook to the node. Those are all hooked up. Okay. What I'm going to do is I'm going to make my A input to be half speed of my B input, which means my pulse is going to be 6 nano, and my period is going to be 12 nano. In a SPICE simulator, I don't like to put seconds in here because it's implied. Keep those at 6 and 3. Alright, so we have all of our simulations set up. Control 9 to zoom out. F5, 0 errors and warnings. This is very good. Makes me very happy. Alright, if I say F4, running SPICE, I'm on Linux right now, so your SPICE command is a little different. And if you see what these windows were, it says, oh, can't find the model definition, blah, 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 all this stuff. Okay. What we need to do is need to add some miscellaneous SPICE code. Zoom in here, Control I, click on multi-line text. I need a power supply. It's going to go from node VDD to node 0, and it's 5 volts. And I need to dot include c5.txt, which is the file that includes our whatever they call them, transistor models. So I'm going to put that in the upper left corner. My anchor keeps everything left justified, and that's nice. No, I wanted the upper left. There it is. Alright. Now I'm going to add some SPICE code right here. Oop. I'm going to copy and paste it here because it has the same settings. Edit these, and now I'm going to do a transient transient simulation, if you recall, which I hope you do, go from 6, we had a period that was 12. So let's go for 2 of those periods, and I'm going to round up to 25 nanoseconds. We're using LTspice, so we don't need time steps or anything. LTspice does the right thing, and it's awesome. Multi-line text, remember that right there. And this is good for now. F5, because I'm paranoid. F4 runs Spice, and here we go. Runs LTspice. Give you a short tour of what's in here. Okay, so this is a subcircuit. You can think of this as a function definition. This is the definition of the function. GND and VDD are global nodes. LTspice will hook GND to node 0. It says they're the same thing. We're also going to check that our transistor sizes are proper. L is 0.6 microns. Our scale, or lambda, is 300. So 300 times 2 is 600, or 0.6 microns. The first character here in X means call your function, call the subcircuit. What subcircuit? This is just the name of that instance. These are the 2 nodes, and then this is the name of it, delay sims INVX1 out. Alright, so that's how we do that. We have a bunch of transistors here in our subcircuit, X subcircuit. Way down here, this is just a directive saying we have some nodes that show up everywhere. Here's our 2 pulses. Here's our a whole bunch of inverters. Do you notice how these inverters was 3, 2, 1, 0? Electric does this, it expands them out. And this is another, that's our XOR gate. Okay, supply includes c5.text. This is in the same location as my simulator. Not simulator. Alright. Okay, plot these. It ran already. Here's A. Hold down Control and B and out. I'm going to check that this is okay. Hey, this is. Here, if I delete this, Control X. Okay, A and B, so A goes 0, 0, 0, 0, 1, 1, 0, 1, 1, and then it repeats again, 0, 0, 0, 1, 1, 0, 1, 1, going through all of our whatchamacallits. If I plot the output, we have low, high, high, low. This is an XOR gate. Do you see this little glitch right here? That is, remember we have inverters in there, there's delays through the inverters, so we have 2 gates, we get a glitch. This is called a glitch, and we might call this, have a contamination delay that we can talk about at other times. I want to measure the delay specifically when our output has a transition. These only happen in right here, and at 9 nanoseconds. I'm going to zoom in so I can get a nice good look at these. Put some cursors on here. Left click on here. Here's my cursors. I'll put my cursor screen up here. I need to go to 2.5 volts. Okay, that's as good as I can get right now. And then I'm going to right click on Vout and attach the second cursor. Right click on Vout, attach the second cursor. I can see its cursor number. Ooh, don't do that. Oh man. Okay, let's zoom back in. Messed up my zoom. Here's cursor number 1. I'm going to go to 2.5 volts. And 2.5 volts. Okay, it's close enough. The horizontal distance is 227 picoseconds. Okay, that's nice. That's our delay. Remember what that delay is. Okay. I closed LTspice. If I hit F4 again, LTspice starts up, but I don't have the plot. Here's another trick. I'm going to set up my plot. Okay, plot my waveforms, and then I'm going to save the plot settings. This is Linux, and this dialog box is always borked for me. But if you just say the default, which is the same as in Windows, test XOR, which is the same as what we have, save. Okay, close LTspice one more time, start up simulation with F4, and you can see starts up right away. The way LTspice works is if you have a plot settings file that's the same name as your netlist, the .spi file, then it will automatically load those settings. As you can see, you can save with different names if you like to have different sorts of plot setups, but this is the one that will load automatically. What we want to do is I want to do some measurements and make them automatic. So I'm just going to use these, remember, multi-line text. In Spice, there's these commands. This is a dot command to do a transient simulation. These measurement commands. Let's see if I can put these all up at the same time. Okay. I'll leave that there. I'll run my simulation. Oops, F4. Here's LTspice simulation. I'm going to make this window smaller. And these are the two delays right here that I want to see. Alright? Now, I want to zoom from here to 0, because 0 is where a simulation starts. You'll see why in a second. Snap that up here, Control I. Can I show LTspice? Perfect. Perfect. Alright, multi-line text, remember that. I'm going to do a measure command. Here we go. I'll talk about it as I do it. Dot measure. Transient simulation, because we can do many sorts of simulations. The name of my variable, I'm going to call this TPH, because I'm going to go for this edge right here. The output is rising. Then we put an H suffix on there. I'm going to trigger when the voltage at B is 2.5. Okay, and then it needs to be the first, it's rising, it needs to rise through that. This is like trigger on an oscilloscope, and in the simulation this is the first time that it rose. My target is voltage of node out, voltage at node out, at the value 2.5 volts. I don't need the suffix because this is volts. And it is also the first time it rose. I'm going to copy this. And now we can do the other time. You can see it over here, way over here. This is TPL. Okay, TPL. Trig VB 2.5 when it rises. No, actually when it is when it rises. Alright, so when B rises, so this stays the same. Target when V out goes by 2.5, but this time it's falling. We have to go all the way back to the start of the simulation. It is the first time it has fallen. It's very important. If you get these rise and fall numbers, you'll get negative numbers or measure a period instead of a rise time and such. Alright, so we say OK, close that. Here's my measurements that show up. This is part of my circuit. These are part of my analysis. That's why I keep them in different places. And we're at 19 minutes. It's worth it. F4, run the simulation. Here is the simulation, okay? Now we can let's measure this again really quickly with our cursors. This would be TPH is what we called it. Oops. Cursor number 1 at 2.5. Do 2.5, close enough. And second cursor, I right clicked on here. There's 2, and it is 2.5, and we had 230 picoseconds. Remember that, because I'm going to go to View, Spice Error Log. I can't show these at the same time. And look, this is where my data shows up. Some stuff, but this is where your measurements show up. TPH, 2.29 times 10 to the minus 10, which is 10, 11, 12. This is 229 picoseconds. We cursored it to be 230. This is right on. If we went over to the other side, we would see that this is 6.12 nanoseconds. I think this measured it in the wrong spot because it goes, I'm going to see how this goes from 3.0 to 3.3. It does. Oops. Beep. Can I cursor over? No, of course not. Alright, so I'm going to zoom to this one. And we really need to go from 9 something nanoseconds to 9 point something nanoseconds. You'll notice that that did not show up in the SPICE error log. It went from 3 to 9, which is why, of course, the difference was 6. But this number is bogus. Bogus! Let's close it down. Go back to our Control-I. Rise, fall, fall, fall. Oops. I need to run the simulation so I can see the waveforms. So this would be, so B is rising. I'm looking at this thing. B is rising. Okay, out fell. There we go. Out fell, but B was the second time that it rose. See how this? It goes down, up, down, up. So this is the first second up. So we can change that to be rise equals 2. See how I'm debugging this? Say OK. F5 because I'm paranoid. F4 to run the simulation. Showed up in the wrong window. I mean, it's the same simulation, but we're going to look at the error log from 9 to 9. This is a good one. So 105 picoseconds. 229 stayed the same, but is 105 legit? Well, if you don't believe it, you can zoom in. Need some more coffee. Alright, stick a cursor at 2.5. Stick the other cursor at 2.5. Don't make these videos for entertainment. And it's 100 something picoseconds. Exactly what the error log said. That's how you can measure some delays. If you want to measure rise time and such, you can probably figure out that this number, this value can be changed. This could be, say, 10% to VB at 90%. Just as a hint. Thanks for watching.